In this video, I'm going to talk a little bit about the results of the unbalanced torque lab you did, and especially what's the significance of the slope we got. So first up, when you make a graph of torque versus angular acceleration, we ended up with some nice straight lines. So if we turn that slope into a for every statement, in this case, that slope is telling you how much torque you need for every 1 radian per second squared of angular acceleration. Now this turns out to be really closely related to a lab we did earlier this year with unbalanced forces. We made a graph of force versus acceleration, and we got a nice straight line, and we said that that slope is telling us how much force you need for every 1 meter per second squared of acceleration. So we have these really similar for every statements. We ended up defining the slope of this force versus acceleration graph as the inertial mass. So inertial mass, that's a measure of how difficult it is to accelerate an object or to change its motion. We're seeing a really similar idea here for rotation. Since torque causes angular accelerations, it changes the angular motion of an object. And so an object has some amount of resistance to changes in angular motion. And we're going to call this rotational inertia. So rotational inertia is how difficult it is to change your angular motion. And so you probably saw that when people did or collected data for different wheels in the labs, they got different slopes, because those wheels have different amounts of rotational inertia. Now, rotational inertia is sometimes referred to as moment of inertia. I know those of you who are in multivariable calc saw that phrase earlier this year. Moment of inertia is a really kind of confusing phrase, so it's being used less and less. And rotational inertia is really taking over. That's what you're going to see on the AP exam if they have questions about this, is rotational inertia rather than moment of inertia, but they do refer to the same thing. So now to help with getting to some ideas about rotational inertia, I want to go through the units on this slope. So torque has units of newtons times meters, and then your angular acceleration has units of radians per second squared. Now in physics, radians tends to be treated as not really a unit, and so this is going to turn out to be newtons times meters times seconds squared. Now I can simplify this a little bit farther, because a newton is also a kilogram times a meter per second squared. So if I go back up here, instead of a newton, I'm going to write a kilogram times a meter per second squared, and then I have meters again, and then times seconds squared. So these seconds squared are going to cancel, and I end up with units of kilograms times meters squared for rotational inertia. So what that leads me to is that rotational inertia depends on how much mass and how it's distributed. So where that mass is. And so different shapes are going to have different rotational inertias, even if they have the same mass. Now, in general, rotational inertia, which we're going to represent with a capital I, is related to mass times the radius squared. And that's how we get that unit of kilograms times meters squared. Now, there's always going to be some number that goes in front of the mass times radius squared, but what that number is depends on the shape. So a ring has a certain number times mr squared. A solid sphere is going to have a different number times mr squared to be able to find rotational inertia. The good news is you don't really have to know that for this exam. In AP Physics, if you have to calculate the rotational inertia of an object using its mass and radius, it's going to give you the coefficient for that shape, if not the full equation for the rotational inertia. So all you have to know is that increasing the mass and increasing how spread out the mass is. So increasing that R so that the mass is further from the center of mass is going to increase the rotational inertia. Now, rotational inertia is something that it can be really powerful to directly feel. And so I'm just going to show you a couple of quick things that you might be able to try at home that let you see what or feel and experience directly changing the rotational inertia. So for one option, I've got a cutting board. Anything kind of long and flat will work. And I've got some canned pie filling. Just about anything heavy will work. And what you can try is try lifting it with the heavy thing at the end. And you can try lifting it with the heavy thing near your hands. Now, when I hold it, or when the can is near my hands, this mass isn't very spread out. Most of the mass is pretty close to the axis of rotation. So it's got a relatively small rotational inertia that makes it fairly easy for me to hold this and rotate it. On the other hand, if I put it down at the end, the rotational inertia gets a lot bigger. The mass is much, much more spread out from that axis of rotation. So this all of a sudden has a much bigger rotational inertia, and I can feel this is much heavier. I need two hands to rotate it instead of just one. Another option you can try is if you have something relatively long, a yardstick, a broom handle, anything like that'll work. I've got a piece of PVC pipe here. And then if you have a way to put something heavy on the end, I happen to have some ankle weights around. And again, if I put it far away near the end of the thing, so it's far away from the axis of rotation, it's pretty hard for me to lift, for me to rotate this. I need to apply a lot of torque to get an angular acceleration. If I move this really close to my hands, all of a sudden it's super easy for me to rotate. I've got a smaller rotational inertia, so I need less torque. I don't have to use as much force to rotate it.